The following linear second-order non-homogeneous ordinary differential equation models an engineering problem. Our differential equation is second-order non-homogeneous, which means at the right-hand side we have a function, a constant function. U0, the initial conditions, U0 is equal to 0, and the derivative of U evaluated at 0 is also 0. We want to solve this differential equation using Laplace transform. Before I delve into the details, the definition of the Laplace transform is this one, is the integral from 0 to infinity of the function f of t, where the transform is acted on, times e to the minus s times t dt, where s is strictly positive. Some useful relationships before we proceed to solve this differential equation is the following. When we take the Laplace transform of a constant function, this is going to give c over s. If we want to go backwards, we take Laplace inverse of c over s and we get back the constant function c. If we have the Laplace transform of the exponential to some scaled power a to the power e to the power of a times t, so here you have a scaling, this is 1 over s minus a. The Laplace transform of the this exponential is 1 over s minus a. And if you want to go backwards, you take the inverse Laplace transform of this quantity and you will get your function of time back. If you want to take the Laplace transform of this exponentially decaying function, this is going to give you 1 over s plus a. So here is a minus, here it's a plus, and here is a plus, here's a minus. You take the inverse Laplace transform of 1 over s plus a, this will give you the exponentially decaying function. Okay, so let's go to our problem. U second derivative plus 3u first derivative plus 2 times the function u is equal to 1. We take the Laplace transform on both members of the equation. The Laplace transform is linear, so it will act on each one of the terms. Plus 3 Laplace u prime of t plus 2 Laplace u of t equals Laplace of 1. The Laplace transform of the second derivative is s squared, is s to the power of 2 because second derivative. U of s, my new variable, is a function. My capital U is the Laplace transform of the function u of t, and s is my new variable, plus 3 times the Laplace of the derivative of the function is s times u of s, plus 2 the Laplace of this one, so this is the Laplace of this one is s squared u of s. The Laplace of this one is s u of s, and the Laplace of u of t is capital U of s, equals, as we said before, the Laplace transform of the constant function is 1 over s. We can take common factor u of s, and we have s squared plus 3s plus 2 equals 1 over s. Now I solve for u of s, and I have 1 over s squared plus 3s plus 2. Now I need to factorize the quadratic s squared plus 3s plus 2. So I need the roots of this. S1 is minus 3 plus the square root of 1 over 2. S2 is minus 3 minus the square root of 1 over 2. So this can be written as s squared plus 3s plus 2 as 1 times s minus s1 times s minus s2. So it's gonna be s plus 1 times s plus 2. So this guy here is 1 over s times s plus 1 times s plus 2. Now the next step is using analysis into partial fractions. So my u of s is 1 over s times s plus 1 s plus 2. I break that into partial fractions as s plus 1 s plus 2. A over s plus b over s plus 1 plus c over s plus 2. Now I multiply with the least common multiple, which is s times s plus 1 times s plus 2. Okay, now I can get rid of this, and at the left hand side I have just 1. I can simplify this, s, and I have as plus 1 s plus 2 plus bs s plus 2 plus cs s plus 1. Now I have to work things out at the right hand side. Let's collect the terms that involve the s squared. A plus b plus c s squared plus 3a plus 2b plus c times s plus 2a. From here I have to match the coefficients of the right hand side to the coefficients of the left hand side. So a plus b plus c is going to be equal to 0 because I don't have any s square at the left hand side. 3a plus 2b plus c is going to be equal to 0 because I don't have any term involving s at the left hand side. And 2a is going to be 1. So from here a is going to be equal to a half. Now let's go and substitute a back into 1 and 2. So I have so I have b plus c equals minus a minus a half, and here I have 2b plus c minus 3 halves. I solve this linear system, so I subtract by parts, and I have b plus c minus 2b minus c equals minus a half plus 3 halves. I can get rid of these terms and I will have minus b at the left hand side of the equation equals 4 over 2 2 over 2, sorry, 3 minus 1 is 2. So minus b is going to be 1, b is going to be minus 1, b is going to be minus 1. I also have a Let's go to the first one and find what is c. C is gonna be minus a minus b. So this is going to be minus a half plus 1. So it's gonna be equal to a half. It's gonna be minus a half minus minus 1, and that's c is gonna be equal to a half. Okay, now let's go to write u of s. It's gonna be a over s plus b over s plus 1 plus c over s plus 2. And I have that a is 1 over 2, so it's 1 over 2 times 1 over s minus 1 over s plus 1 plus 1 over 2 times 1 over s plus 2. Now, in order to find u of t, I take the inverse Laplace transform of u of s. So it's a half the inverse of 1 over s minus the inverse of 1 over s plus 1, the inverse Laplace, plus a half inverse of 1 over s plus 2. So my u of t is going to be a half, because Laplace inverse of 1 over s is just 1, minus Laplace inverse of 1 over s plus 1 is e to the power of minus t, plus a half times 1 over s plus 2 e to the power of minus 2t. So my u of t is going to be a half minus e to the minus t plus a half e to the power of minus 2t. That is my final solution.